Now, in this video, we are going to find out the important parameters for the simulation. So, as you know that the Reynolds number is equal to 100 for this simulation. And you know that when Reynolds number is less than 2300, the flow is laminar. And when Reynolds number is greater than 4000, the flow is turbulent. And in between them we have the transitional flow. So definitely this is the case where the flow is laminar because it is less than 2300. Okay, so we also know that the formula for Reynolds number is equal to rho v. That's a very average velocity, and for the pipe this will be diameter. Otherwise, this can be the length or this can be the chord length even for aerofoils, and divided by mu. Okay, so far we know that this thing that we have the from entrance length derivation are the formulas. We know that okay, so we have derived these, like we have these formulas for entrance length, and then we derive these equations. Okay, so from this formula you know that we have taken the values for the entrance length 5, and then we also taken the 5 for the fluid developed flow, and then we multiplied with the factor of 4 because we want to make the simulation maybe generic to the other Reynolds number also, and also we want to be on the safe side that the flow is fully developed when we analyze the flow in some section. So we know this thing that diameter is equal to 1 meter. So we can write down diameter is equal to 1 meter. The Reynolds number is 100. And now we will assume the few things here because in CFD we can assume like any property that is not practically possible in wind tunnels or in the labs. And also I want to assume the velocity, that can be the u. You can write it as a u also. So let's put it in this way. So u is equal to 1 meter per second, and diameter is equal to 1 meter, and length of the pipe we have taken is the 40 meters. So this means L by D is equal to 40. Okay, so we have taken the u is equal to 1 meter per second, and also we are assuming the density of the fluid is equal to 1 kilogram per meter cube. So now only remaining term in the equation is the mu, and now we cannot take the any value for the mu because we want the ratio of these all terms should be equal to Reynolds number, and it should be equal to 100. So we cannot take the value of mu randomly. It should be calculated now from the formula. So we can calculate the mu from formula as rho u d upon the Reynolds number. So put the values, and this is equal to 1 into 1 into 1 divided by 100, and this is 0.01 Pascal second. Okay, now we have all these properties. So let me summarize that we have the Reynolds number is equal to 100. The length of pipe is equal to 40 meters. Diameter is equal to 1 meter. And the fluid properties like density is equal to 1 kilogram per meter cube, and the viscosity is equal, and this is dynamic viscosity, this is equal to 0.01 Pascal second, and also the boundary conditions are velocity is equal to 1 meter per second. Okay, one more thing that I want to discuss here. Sometimes you may see the different units in the fluid. So the main units we use is a Pascal second for viscosity. So now let's dig in more into the Pascal second. This is like Newton per meter square into second. And now you know that the Newton, the force is equal to m into A. So we know that the units would be the kilogram into meter per second square. So kilogram meter per second square and into 1 upon meter square, that is over here, into second. So you can write down the second in SES. It's more easy to understand here. And 1 meter will be cancelled out from here as well. This is going to be the kilogram per meter per second. And just to give you idea that when you go through simulation part, the CFD simulation part, so I have already opened the fluent simulation for pipe flow, and same properties which we drive right now is they are in put into this panel here. You can see the viscosity units are kilogram per meter second. This is the same thing, that is kilogram per meter second. So they are equal. So when discuss about viscosity units, Pascal second, and when you see the kilogram per meter per second is the same thing. So now we have all the required conditions, properties, geometry for this simulation. So let's start with the actual problem. And before that, I want to give you some theoretical calculations.